In this video, we will be looking at limits at infinity. Okay, so if the values of f of x become arbitrarily large, arbitrarily close to L as x becomes sufficiently large, we say f has a limit at infinity and we'll write this. Right, read the limit of f of x as x approaches infinity is equal to L. Next definition is practically identical. If the values of f of x become arbitrarily close to L as x becomes sufficiently, here's one difference, large negative, and here's the second difference. It's a limit at negative infinity. And we write, and of course this is going to be different. All right, so this is read, limit of f of x as x approaches negative infinity is equal to L. Now, with these two definitions, we can formally define what is meant by a horizontal asymptote. If the limit x approaches infinity of f of x equals L, or the limit x approaches negative infinity, f of x equals L, we say the line y is equal to L is a horizontal asymptote of f. Now a quick comment about asymptotes. By its very definition, right, a function can never cross vertical asymptotes. Right? So function can never cross vertical asymptotes. Right, because remember that a vertical asymptote was when the limit as x approaches a of the function was plus or minus infinity, or one of the one-side limits was plus or minus infinity. So for a graph, if we just look, it would be something like this, let's say. Right, so this was a vertical asymptote. And actually, so is that and that. We could, however, have it touching the asymptote, right? We could have a piecewise, and then that could do something like, I don't know, that. Right, that's not a violation. right? But if it were to cross it, it would now be a violation because you wouldn't have an infinite limit on one of the sides of the asymptote. However, there is no such restriction on horizontal asymptotes, right? So a function can cross a horizontal asymptote, and theoretically it could cross it an infinite number of times. Right, if we take a look, let's say this will be our horizontal asymptote. We can have a function that does this. Right, as long as, and if we look out in the long run, the limit is approaching the asymptote, then we're fine, right? So horizontal asymptote you can think of as end behavior of the function. Two more definitions to look at. Right, so we say a function f has an infinite limit at infinity. And we write that if f of x becomes arbitrarily large as x gets sufficiently large, and the second definition, practically identical. Except it's now a negative infinite limit at infinity. And this time we write this if f of x is less than 0 and the absolute value of f of x becomes arbitrarily large. As x gets sufficiently large. And similar definitions can be formed if x is approaching negative infinity. We now conclude with several examples. First, let's look at this function here. So f of x, 5 minus 2 over x squared. As we did when we first started looking at limits, we will create a table of values. First, we're going to let x grow sufficiently large. So first we want x equals 100. Go away, keyboard. So let's go ahead and load up a calculator. Okay, so our function f of x was 5 minus 2 over x squared. Let's go ahead and store that function. All right, so the first thing we wanted was f of 100. All right, so notice that it's giving me a fraction. It's giving me an exact value. I don't want an exact value. There are two ways to fix this. First way is just to do Control-Enter, which gives an approximation. The second way I could have done it was to just put a decimal point after the 100 and then just hit Enter. So we get 4.9998. All right, let's now move on to 1,000. All right, so let's add an extra 0. 4.999998. How many nines is that? It's 5 nines. Right, so and let's do one more. Let's look at 10,000. And so again, basically all we're doing is adding an extra 0. Now there's 7 nines. What we should notice is the limit as x approaches infinity of f of x. So as x continues to get larger, it appears that f is stabling out to the value of 5. We want to do the same thing, except now we want the negatives. So what we're now doing is creating a chart for x approaching negative infinity. I will use the exact same values except they're negatives, right? So negative 100, let's recall that and just put a negative out in front. Same value. And instead of switching back and forth, I'm going to show you right now that negative 1,000 gives you the same as 1,000, and negative 10,000 gives the same as positive 10,000. And so we say the limit as x approaches negative infinity of f of x also happens to be 5. Okay? Well, let's now look at this function. Sine of x over x. Oops, let's draw that better. Again, we're going to do positive infinity and negative infinity, so let's start at 100. Come back over to our calculator. Let's redefine our function. And so f of x is now going to be defined sine of x over x f of 100. Make sure I'm in radians, which I am. So negative 0.005, let's say 0.0051. Let's look at 1,000 now. All right, I have it set in scientific notation. So that's going to be let's say 8 preceded by 4 zeros. Let's look at 10,000. That is a negative 3, right? So it'll be a 3 preceded by 5 zeros, and it's negative. That's close enough to 0 for me. I'll just say 0. And let's look at one more. 100,000. Just to see what happens. And so that is a 3 preceded by 7 zeros. So again, that's close enough to 0 for me. Right, so we can say limit as x is approaching infinity. I'm not going to rewrite the function, just f of x appears to be 0, right? So notice that even though the function is oscillating, it's bouncing back and forth between positive and negative values, the absolute value is steadily approaching 0. If we now do the negatives, right, using the properties of trig functions, the fact that sine is odd, we don't even need to create a table. All of the values for f are going to be the same as above. Right, so that is to say, if x is negative 100, f will still be this value. Negative 1,000 will still be this value. So the limit as x approaches negative infinity of f of x also happens to be 0. It follows the same values. Right? And then let's now look at f of x being the inverse tangent of x. Right, we'll start with 100. Right, we need to redefine. So f of x is now trig inverse tangent of x. Again, make sure we're in radians. F of 100, 1.5608, let's say. One thousand. 1.5698, let's say. 10,000. 1.5707. Let's just do one more. Let's look at 100,000. Just for fun. 1.5708. So let's say the limit as x approaches infinity of f of x, 1.570, right? Notice that the change from 10,000 to 100,000 was only in that last decimal place. So we know that up to that decimal place, that's what the limit will be. Now, in fact, this is an approximation. This is actually pi over 2. If we look at the graph of inverse tangent, let x go out to infinity, we'll see that it is approaching pi over 2. What happens as x goes to negative infinity? Well, the fact that tangent is odd means that the inverse tangent is also odd. So all of the values will be the same except they will be negative. So we'll have negative 1.5608. And if you don't believe me, let's come back to our calculator and type in negative 100. Oops. Let's do this one, negative. And you can see it's the same value, just negative. All right, so now negative 1,000 will be this. And I'm just going to do this to say so on and so forth. All the values are going to match, except negatives from the previous table. So limit as x approaches negative infinity of f of x will approximately negative 1.570, which is negative pi over 2. Okay. Now let's look at how to evaluate limits at infinity algebraically. So let's first consider the function f of x equals 3x minus 1 divided by 2x plus 5. Okay? We want the limit as x approaches infinity of f of x. So what we're going to do is look at the denominator. Take the largest term in the denominator, which in this case is 2x, and we will divide everything by x, right? So we're going to divide everything by, go away keyboard, by this highest power. So we'll have 3x over x minus 1 over x all over 2x over x plus 5 over x. And what we're going to do is also make use of the fact, and this is very easy to see just from a graph, that limit as x approaches infinity, actually it's limit as x approaches plus or minus infinity of 1 over x to any power n is 0. And I should specify n greater than 0. And it's a real number. So for any positive real number, which can also be represented this way. Right now, of course, remember the limits. There's one more step I want to do, right? Simplify as much as possible, right? So 3x over x becomes 3. Two x over x becomes 2. Now, using the fact that the limit can be split across quotient, addition, subtraction using the limit laws, that limit will go to 0, that limit will go to 0. So we're left with 3 over 2 as our limit. And we're going to do similar analysis now for negative infinity. But I'm not going to rewrite all of the work, but we're doing the exact same thing as we did up here. So we're going to be left with 3 minus 1 over x over 2 plus 5 over x. Right, then using this property up here in green, that goes to 0, that goes to 0, and we're once again left with 3/2. All right, let's look at limit as x approaches infinity now of 3x squared plus 2x all over 4x cubed minus 5x plus 7. We again want to take the highest power of x in the denominator and divide every term by it. So in this case, it's x cubed. All right, and now simplify as much as possible. Limit x approaches infinity, so we'll have 3 over x plus 2 over x squared over 4 minus 5 over x squared plus 7 over x cubed. And then using that property written in green before, that'll go to 0, that'll go to 0, that'll go to 0, that'll go to 0. We're left with the limit as x approaches infinity of 0 over 4, which is just 0. If we now look at x approaching negative infinity, again, the analysis will be the same. So we'll have the limit as x approaches negative infinity, 3 over x plus 2 over x squared over 4 minus 5 over x squared plus 7 over x cubed. Again, 0, 0, 0, 0. We'll be left with limit of 0 over 4, which is 0. Let's now look at limit as x goes to infinity of 3x squared plus 4x all over x plus 2. So limit as x goes to infinity. Again, we want to look for the highest power in the denominator and divide everything by it. And highest power happens to be x, so 3x squared over x plus 4x over x all over x over x plus 2 over x. Now simplify. We'll have 3x plus 4 all over 1 plus 2 over x. That goes to 0. However, this term here, this 3x, will go to infinity. Right? So essentially we have an infinite number divided by 1, which is infinite. So that is infinity. Limit x approaches negative infinity. Same analysis. So this becomes limit as x approaches negative infinity of 3x plus 4 over 1 plus 2 over x. Right? The 2 over x will go to 0, but now the 3x goes to minus infinity. Right? And so our limit would be negative infinity. Let's now look at limit as x goes to infinity of 3x minus 2 over the square root of 4x squared plus 5. We again want to look for the highest power in the denominator. It happens to be the square root of x squared, which is the absolute value of x. All right, so if we factor out an absolute value of x from the denominator, essentially what we're doing is factoring out this x squared, which will leave us with the square root x squared times 4 plus 5 over x squared. Right, and the square root of x squared is absolute value of x. Applying that absolute value of x term to each term in the numerator will leave us with this, 3x over absolute x minus 2 over absolute x all over this square root. Now, the absolute value of x. That absolute value is important. Since x is approaching infinity, that means all the values of x will be positive. So the absolute value of x becomes positive x. All right, so this becomes limit x approaches infinity of 3 minus 2 over x all over that square root. 3 over x will go to 0, 5 over x squared goes to 0. What we are then left with is the limit of 3 over root 4, which is 3 over root 4, which is 3 halves. Let's now look limit as x approaches negative infinity. Well, the analysis will be the same up to here. So we write this as the limit x approaches minus infinity of 3x over the absolute value of x minus 2 over the absolute value of x all over the square root of 4 plus 5 over x squared. Now, since x is approaching negative infinity, that means all the values of x are negative. So the absolute value of x becomes negative x. So this will become the limit x approaches negative infinity of negative 3 plus 2 over x over that square root. 2 over x still goes to 0, 5 over x squared still goes to 0. We are then left with negative 3 over root 4, which is negative 3 halves. All right, so limit as x approached positive infinity was the 3 halves up here. Go away, keyboard. And limit as x approached negative infinity happened to be negative 3 halves. Let's now look at one final example. Limit as x approaches infinity of 2 plus 3e to the x over 7 minus 5e to the x. want to do something very similar. We want to look for the largest term in the denominator and divide everything by it. Well, the largest term in the denominator is this, go away keyboard, is this e to the x. So we're going to divide everything by it, so we get 2 over e to the x plus 3e to the x over e to the x divided by 7 over e to the x minus 5e to the x over e to the x. So we get the limit as x approaches infinity of 2 over e to the x plus 3 divided by 7 over e to the x minus 5. Now the idea here is the same. Limit as x approaches infinity of e to the negative x would wind up being 0. So we're left with negative 3 over 5. Now, we want x going to minus infinity. Here, there's no need to worry about dividing by anything, right? Because we can write it this way. Since x is going to negative infinity, just write it as 2 plus 3 over e to the negative x, and then 7 minus 5 over e to the negative x. Well, this is the same as limit as negative x goes to infinity, right? If x is going to negative infinity, then negative x is going to positive infinity. Well, now that leads to the same thing. This term goes to 0, this term goes to 0, and we're left with 2/7. Now, later on in this lecture series, probably about halfway through, we will study a different technique of evaluating these types of limits. But for now, that's how we're going to be dealing with limits at infinity. So that concludes this video on limits at infinity. The next video in this series will give the precise definition of a limit.